Have you ever wondered who discovered gravity? The story of an apple falling from a tree leads to one of the greatest scientific discoveries of all time. This discovery was made by Sir Isaac Newton, one of the most brilliant scientists in history. He was a mathematician, physicist, and astronomer who changed the way we understand the world. Today, I will talk about his life, discoveries, and lasting impact on science. Isaac Newton was born on January 4, 1643, in Woolsthorpe, England. He was a small and weak baby, and his father died before he was born. When his mother remarried, he was left with his grandmother as a child. He was very curious and loved to build models of windmills and clocks. He later went to the University of Cambridge, where he became deeply interested in mathematics and science. During the Great Plague, he had to leave Cambridge and study at home. It was during this time that he developed some of his greatest ideas. Now, let's talk about his most famous contribution to science. Number 1. Laws of motions and gravity. Newton is best known for his 3 laws of motions. The first law states that an object will remain at rest or in motion unless acted upon by a force. The second law of explain that force equals mass times acceleration. The third law tells us that for every action, there is an equal and opposite reaction. He also formulated the law of universal gravitation, which states that every object in the universe attracts every other object. The famous apple story is often used to explain how he discovered gravity. Number 2. Newton developed a new branch of mathematics called calculus. This helps solve problems related to motions and chains, which is still widely used in science and engineering today. And the last one is number 3, optics and light. Newton also made important discoveries about light. He showed the white light is actually made up of different colors by passing it through a prism. He also invented the first reflecting telescope, which allowed astronomers to see objects in space more clearly. In 1687, Newton published his most famous book, Philosophiae Naturalis Principia Mathematica, also known as Principia. This book explains his laws of motions and gravity and is considered one of the greatest scientific books ever written. Newton later became the president of the Royal Society and was in charge of England's currency as the warden of the Royal Mint. He was knighted by Queen Anne in 1705. Becoming Sir Isaac Newton, he continued his scientific work until his death on March 31, 1727. Isaac Newton's discoveries changed the world. His laws of motion, gravity, and calculus continue to be used in science, engineering, and space exploration. He once said, "If I have seen further, it is by standing on the shoulders of giants." Today, we can say that many scientists have stood on his shoulders, using his work as a foundation for new discoveries. His legacy lives on, making him one of the greatest scientists in history.
Now we delve into the most groundbreaking scientific concepts of the 20th century, Albert Einstein's theory of relativity. Einstein's insights revolutionized our understanding of time, space, and gravity, paving the way for modern physics. And so this report, we will be explore the two pillars of relativity, special relativity and general relativity. So the part 1 is special relativity. In 1905. Einstein published his special theory of relativity, fundamentally altering how we perceive motion and time. The key of principles, especially relativity, include: number 1, the principle of relativity. The laws of physics remain the same for all observers moving at constant speeds relative to each other. Number 2, the speed of light. The speed of light in the vacuum is always constant regardless of the motion of the observer or the source of light. And the third one is the time dilation. As an object moves closer to the speed of light, time for it slows down relative to an observer at the rest. And the fourth one naman is length construction. Moving objects appear shorter in the direction of motion when approaching light of speed. Now, the part 2 of our topic is general relativity. In 1915. Einstein expanded his theory to include gravity, introducing general relativity. This theory describes gravity not as force, but as the curvature of space-time caused by mass. The key ideas include: number 1, space-time curvature. Massive objects like planets and stars bend the fabric of space-time, creating what we experience as gravity. And the number 2 is gravitational time dilation. Time runs slower in stronger gravitational fields, an effect observed near black holes. And the number 3 is gravitational lensing. Light bends around massive objects, allowing astronomers to observe distant galaxies. And the number 4 is predictions and confirmations. So the bending of the starlight by the sun detected during the 1919 solar eclipse confirmed Einstein's theory and made him world famous. So the impact and application of Einstein theories have led to numerous real-world applications, including GPS technology, which corrects for time dilation effects, understanding black holes and gravitational waves, advancement in space travel, and astrophysics conclusion. Albert Einstein's theory of relativity transformed science and technology, influencing everything from quantum mechanics to cosmology. His works remains a foundation for modern physics and continues to inspire new generation of scientists.
Standard model or particle physics is a statistical framework that describes the behavior of fundamental particles and forces in the universe, encompassing 17 fundamental particles, including quarks and leptons, and 3 fundamental forces. So we have electromagnetic, weak nuclear, and strong nuclear, while also explaining the particles acquire mass through the Higgs mechanism. Theory proposed that the fundamental buildings blocks of the universe are not particles, but tiny vibrating string that exist in a space-time continuum with 10 dimensions, of which are familiar 3 dimensions, of which space and 1 dimension of time are just subject, while the remaining 6 dimensions are curled up or compactified, so tiny that they're not directly observable.
Radioactivity is the process by which unstable atomic nuclei lose energy by emitting radiation in the form of particles or electromagnetic waves. There are 3 main types of radiation, which is the alpha particles, beta particles, and the gamma rays. The alpha particles is a high-energy helium nuclei that can travel a few centimeters in air. The beta particles is high energy electrons that can travel several meters in air, and the gamma rays is high energy electromagnetic waves that can travel long distances. Radioactivity has various applications including medical treatment and scientific research. The medical treatment is cancer therapy, imaging, and diagnostics. And the scientific research naman is understanding nuclear reactions, dating ancient materials, and studying cosmic phenomena. So let's proceed to quantum mechanics. Quantum mechanics is a branch of physics that focuses on the behavior of matter and energy at an atomic and subatomic level. At these scales, the classical laws of physics no longer apply, and strange, seemingly random phenomena govern the behavior of particles. There are key principles of quantum mechanics include wave-particle duality, uncertainty principles, and superposition, and entanglement and quantization. Number 1. Wave-particle duality. Particles such as electrons can exhibit both wave-like and particles like behavior. Number 2. Uncertainty principles. It is impossible to know certain properties of a particle, such as its position and momentum, simultaneously with infinite precision. Superposition. Particles can exist in multiple states simultaneously, which is known as a superposition of states. Entanglement. Particles can become entangled in such a way that the state of one particle is dependent on the state of the other, even if they are separated by large distances. Quantization. Energy comes in discrete packets or quanta rather than being continuous. Quantum mechanics has been incredibly successful in explaining many phenomena that were previously unexplained, such as the behavior of atoms and molecules, the properties of solids and liquids, and the behavior of light. Some of the key applications of quantum mechanics include transistors, lasers, computer chips, magnetic resonance, quantum computing. Transistors, the building blocks of modern electronics, which rely on the principles of quantum mechanics to control the flow of electric current. Lasers, devices that produce intense, coherent beams of light, which rely on the principles of quantum mechanics to amplify light. Computer chips, the processors that power modern computers, which rely on the principles of quantum mechanics to perform calculations. Magnetic resonance, or MRI, a medical imaging technique that uses the principles of quantum mechanics to create detailed images of the body. Quantum computing, a new and rapidly developing field that uses the principles of quantum mechanics to perform calculations that are beyond the capabilities of classical computers.
Real-life application of physics. So what is real-life application of physics? So physics is all about how things work. It's not just school subjects. It's the reason lots of things we use every day exist. Number 1. So sa number 1, energy engineering. So think about bridge, buildings, and cars. Engineers use physics to make sure they are strong and safe. They need to know how much weight things can hold and how to build things that won't fall down. So number 2, in energy. So number 2, energy. Your phone, computers, and TV all works because of physics. The tiny parts of inside how they communicate. And even the screen showing pictures use physics. So number 3, technology. Technology, solar panels, windmills, and even nuclear power plants all use physics. To make electricity, they use the power of the sun, wind, or atoms to create energy that we can use in our homes and cities. So physics is everywhere. It's the science behind the things we build and the power we.
Application of physics in real-world industry. Physics plays a vital role in advancing various industries, transforming the way we live and work. This report highlights the significant contribution of physics in two key sectors, transportation and medicine. Now let's discuss the transportation. Transportation physics is instrumental in the development of cutting-edge transportation technologies. Aerospace, rocket propulsion, physics principles such as Newton's laws of motion and thermodynamics govern rocket propulsion system. And these pictures are examples of aerospace. Aerodynamics, understanding airflows, drag, and lift is crucial for designing efficient aircraft and spacecraft. This is the example of aerodynamics pictures. Now let's proceed to automotive. Engine performance. Physics informs engine design, optimizing power output, fuel efficiency, and emissions. In this example of engine pictures. Safety features. Physics-based simulations and testing ensure the effectiveness of airbags, anti-lock braking system or ABS, and electronic stability control or ESC. Medicines. Physics is revolutionizing medical diagnosis and treatment. Into radiation therapy. Cancer treatment. Physics-based radiation therapy targets cancer cells while minimizing damage to healthy tissues. And this is our example of radiation therapy machine. Linear accelerators. Physics principles govern the operation of linear accelerators, which generate high-energy radiation beams. Magnetic resonance. Understand the principles of magnetic resonance enable the development of advanced MRI techniques. Into conclusion, physics plays a vital role in driving innovation in transportation and medicine. By applying fundamental physics principles, researchers and engineers can develop cutting-edge technologies that transform industries and improve lives. That's all. Thank you.